morning, this is B. Naresh, working as Assistant Professor in ACE Department. And today's topic is Common Emitter Configuration with Characteristics. So, before going to this Common Emitter Configuration, and we know that the transistor contains three terminals, namely that is emitter, base, and collector. And based on those three terminals, we define the three types of the configurations here. One is common base configuration, another one is common emitter, and the third configuration is common collector configuration here. So in this today's session, we are going to observe what is the common emitter configuration and what are the characteristics of the transistor is operated under this common emitter configuration here. So in this case, and what is the meaning of this common? Common emitter means the emitter terminal is common for input side as well as your output side. So that is the reason. Emitter is common to input terminal as well as emitter is a common for output terminal. If the emitter is made as a common terminal, the remaining two terminals are base and collector. So out of these two terminals, we need to identify that one. Which one is acts as input terminal and which one is acts as the output terminal. So from this representation, and we know that the base is acts as the input terminal and the collector is acts as the output terminal. So now we need to make the construction. The base is used as the input side and the collector is used as the output side with respect to common terminal is your emitter. So that is the reason now we are going to configure this common emitter configuration. Then by using this emitter is connected between the collector and the base is known as again common emitter configuration. And the input is again connected between emitter and the base and output side is taken from the collector and your emitter here. So for this case and from this representation we know that the emitter is a common for both the terminals, that is input side as well as your output side. From that we can say that this configuration is called as your common emitter configuration here. While constructing this common emitter configuration, we can consider either any transistor, NPN transistor or your PNP transistor here. That is your choice. You can choose either NPN transistor or PNP transistor here. But here I am going to choose a NPN transistor. By using this NPN transistor, how we can configure the transistor is as acts as your common emitter configuration here. So for this case, let us consider, and this is the NPN model here, and we know that. So whatever the configuration, it contains the three terminals. One is represented as base, one is represented as your emitter, and one is represented as your collector here. And then out of these three terminals, now we need to identify that one. Base is acts as your input side and the collector is used as an output side. With respect to your common terminal is your emitter. And we know that if you observe the symbolic representation, and this is the NPN transistor symbolic representation, base, collector, and emitter. And we know that in an NPN transistor, the current flowing is outside the region here. So that is the reason. This arrow mark shows towards outside the region here. Why? Because of that, in this NPN transistor, so at the emitter side, the majority charge carriers are electron. Hence, the electrons are diffusing from the emitter to the base and the collector. So hence, the current flowing direction is your opposite direction. So that is the reason they represented this. The current flow direction is outside the region in the NPN transistor. Suppose if you want to look at the PNP transistor, and this is a PNP transistor representation, and base, collector, and your emitter. And this is a PNP model, and this is NPN model here. If you observe the PNP transistor, the current flowing direction towards inside the region here. So why? Because of the at the emitter side, the majority charge carriers are your holes here. The holes direction and the current flow direction is the same. But In that, in general, the electron and the conventional current flow direction is your opposite here. So from that representation, in NPN transistor, the current flow direction is outside the region, and in a PNP transistor, the current flow direction is inside the region. And again, now here, how to make this biasing configurations here. To make these biasing configurations here, and we need to satisfy a transistor definition here. And if you observe a transistor definition, we know that it transfers a signal from low resistance input circuit to the high resistance output circuit. We need to transfer a signal from the low resistance input circuit to the high resistance output circuit here. So means that we need to satisfy input side that particular junction is offers a very small resistance, and output side that particular junction is offers the high resistance here. So how we can make this? The input side is offers the low resistance, and the output side offers the high resistance here. But this case, if you recall the principle of PN junction here, so and let us consider this is the PN junction here, and this is the P-type material and N-type material here. Then if you approach the biasing concepts here, let us consider if the P is, let us take, and here this is the P is connected with the positive pole of the battery, and N is connected with the negative pole of the battery. Then we can say that this particular PN diode is operated under the forward bias mode. And we know that when a particular diode is operated under the forward bias mode, it offers a diode forward resistance here. And we know that the diode forward resistance is very small here. So that is the reason. When the diode is operated in the forward bias mode, it offers very small forward resistance here. Similarly, let us consider for the same PN diode, and this is the P-type material, and this is N-type material here. And this the P is biased with the negative pole of the battery with respect to this N side. So means P is connected to negative pole of the battery, and N-type material is connected to positive pole of the battery. Under this biasing configuration, this PN diode acts as your reverse biasing mode. We know that when the particular diode acts as a reverse bias, it offers a large reverse resistance that is represented as your R. But here RR is a very large. Why? Because of that, under the reverse bias, it does not allow the conduction across the PN diode. Means under this reverse bias, the current is represented as your 0. So according to Ohm's law, the current is 0 means the particular diode offers very large resistance under the reverse bias. So by using these two principles here, and we need to identify that when the diode acts under the forward bias, it offers very small resistance. If the diode or PN junction is operated under the reverse bias here, it offers very large resistance here. So by using these two principles, now we are going to make the biasing for this common emitter configuration here. So in this case, so in a common emitter configuration or a common whatever the configuration, we need to satisfy that the input side we need to offer the low resistance here, and output side we need to offer the very large resistance here. So that is the reason, and let us observe the input side. So input side here we are going to use the base terminal here. So where B indication is for base terminal here. So and now we need to check out that which type of material is connected across the base here. The base is connected with the P-type material here, so N's. And here now we need to make the forward bias. So how you are going to make the forward bias as this input here? So means this P is connected to positive of the battery with respect to cathode. We can say that that particular junction is a forward bias. By using the principle, here this B is or base is made with the positive pole of the battery. This base is connected with your positive pole of the battery with respect to this common terminal. The common terminal is your emitter here. So this is the common terminal emitter is a common for input side and your output side. So hence N is connected with your negative pole of the battery. So due to this approaching of this biasing energy between base and emitter, hence this input junction is acts as your forward bias. Due to this forward bias mode, this circuit it offers a very low resistance at the input side here. So due to this biasing of VBB and the input junction is acts as a forward bias here, hence it offers the very small resistance across the input circuit here. Similarly, we need to offer a very large resistance across the output side here. So now we can check it here. So from this configuration, the collector terminal is acts as a output terminal. Now we need to make this in between collector and emitter. We need to offer the very large resistance here. So for this case, the collector is made up with the N-type material here. So hence N is connected with the positive pole of the battery. Now we can look at this one. If N is connected with the positive pole of the battery, then we can say that that particular PN diode is acts as under your reverse bias here. If that particular diode is under reverse bias, we know that it offers very large reverse resistance here. So hence, so here the collector is connected with the positive pole of the battery with respect to your opposite terminal here. Then this output side it offers the reverse a large reverse resistance here. So due to that, again this output side the junction becomes your reverse bias here, and input side we made as a forward bias here to satisfy the transistor principle. So based on this forward biasing at the input side and a reverse bias at the output side, a transistor transfers the signal from the low resistance input circuit to the high resistance output circuit. And here we know that this is the NPN transistor, hence the current flow direction is here outside the region. And this current is divided to base terminal as well as your collector terminal here. So hence those currents are represented with base current and your collector current here. So here now I'm going to replace this NPN with a symbolic representation of the transistor here. So and we know that this is the symbolic representation of the NPN transistor here. And this is collector terminal and emitter terminal, and this is your base terminal here. And input side is a bias with forward bias here through this approaching of the VBB here. And output side we made this reverse biasing with approaching of this biasing energy is your VE. And now to observe the characteristics of this a common emitter configuration, first we need to find out the parameters. What are the parameters we need to measure here? And if you look about the input side, we need to observe then the input current and your input voltage. And similarly, the output side we need to identify the what is the output current and what is the output voltage under this configuration here. So coming to your input side, the input current is measured across the base terminal, hence the input current is represented as your IB. Now we need to measure a output voltage between base and emitter, and that parameter here it is represented as your VBE. So means that this VBE indicates that the potential difference between base and emitter. So means that if you want to plot the input characteristics, we need to plot the graph between input voltage, that is a VBE, and input current is your IBE. So then similarly, suppose if you want to identify the parameters at the output side here. So what are the parameters of the output side here? It is represented as, and here, and from this configuration, the output current is measured across the output terminal, and here the output terminal is a collector terminal. So hence, output current is represented as a collector current, that is your IC. Now how to measure the output voltage? Now we need to measure a output voltage between collector and emitter, that is represented as VCE. So means here this VCE indicates that the potential difference between collector and your emitter. So if you observe this one, VBE and the VCE, the third letter indicates the type of configuration here. So which type of configuration we are using here. So here we represented this configuration is common emitter configuration here. And this letter indicates the type of configuration. So that is the reason. So this is represented as a VBE and VCE. And now we need to find out that how much current is flows across this configuration here. Similarly, if you observe the common base configuration, we observe that the current flowing across the common base configuration transistor is represented as IC is represented as alpha times of I. And similarly, in this case, let us consider if you if you want to define a DC current gain. So we know that how to represent the DC current gain. In a common base, the DC current gain is represented as your alpha. But in this common emitter configuration, the DC current gain is represented as beta, or it is also represented like this beta DC here. So what is the current gain of the transistor? It is defined as the ratio of the output current to the input current here. And from the representation, from the definition of the current gain, it is defined as the ratio of output current to the input current. If you observe this common emitter configuration, which one is acts as the output current here? So here the output current is represented as your collector current, and here it is represented as your input current is represented as your base current. So hence, let us consider the beta or the current gain of transistor under the common emitter configuration, or it is also represented as the DC current gain under the common emitter configuration. It is defined as the ratio of output current, that is output current is collector current, to the input current is IB, means there is nothing but a base current. So from this, we need to define the relation of your output current with respect to your input current, that IC is equal to beta times of your IB. So here I am not consider the reverse saturation current here. Here I consider only the majority charge carrier current. So that is with respect to your input current or input charge carriers current, that is IB in terms of base current here. And from this, IC is represented as beta times of IB. Now, but we need to relate in terms of a standard model of the transistor, and we define that in a standard model here. So why? Because of that, under the construction, we need to derive the current parameters from the standard configuration. From the standard configuration, we derive this IC is equal to alpha times of your I. And based on this one, we need to convert this collector current in terms of your base current here. For this case, if you observe this one, we know that and emitter current is represented as the summation of base current and your collector current here. So I is represented as IB plus IC. And if you want to write this, the standard or generalized current expression in terms of reverse saturation current from the common base configuration, IC is represented as alpha times of IE plus ICBO here. So we know that where ICBO indicates that a reverse saturation current when the collector base junction is here open circuited here, or it is called the reverse saturation current when the collector base junction is here reverse biased here. So if that particular junction is a reverse bias, it offers the reverse saturation current, and that current is represented as your ICBO here. Now I'm going to relay this collector current in terms of your common emitter configuration. So we know that in a common emitter configuration, the output collector current is represented as in terms of only the base current. That is the reason I'm going to rewrite this equation in terms of your base current. So how to write this one here? IC is equal to alpha times of IE is represented as this one. What is the IE representation? The summation of base current and your collector current. So hence, I substituted these two here. IC is equal to alpha times of IB plus IC plus ICB. Just expand these terms. What happens? This is IC is equal to alpha times of IB plus alpha times of IC plus ICBO here. From this, what I'm doing, I'm taking the common terms. This is IC minus alpha times of IC, that is equal to alpha times of IB plus ICBO. And in this relation, if you take the IC as a common term, then this is 1 minus alpha, that is equal to alpha times of IB plus ICBO. Now I'm going to relate this IC, that is alpha by 1 minus alpha into IB plus 1 by 1 minus alpha into your ICBO. And here I'm going to assume let I'm going to relate in terms of DC current gain. So that is the reason. The beta, I'm assuming that alpha by 1 minus alpha. Hence, this relation I'm going to rewrite here. IC is equal to alpha by 1 minus alpha. Here I assumed as your beta, DC current gain. So beta times of IB plus. How to write this one? 1 by 1 minus alpha means, here I'm going to write like this. 1 plus beta means 1 plus beta means alpha by 1 minus alpha. If we simplify this one, what happens? This is 1 minus alpha plus alpha by 1 minus alpha. Alpha is get cancelled, that is equal to 1 by 1 minus alpha. Hence, so we know some relation. So 1 by 1 minus alpha is equal to 1 plus beta here. We know some this relation. 1 by 1 minus alpha is equal to 1 plus beta. So hence, 1 by 1 minus alpha, I'm going to write this is 1 plus beta into your ICBOE. So this is a collector current expression in terms of your current gain, DC current gain. So in terms of as well as your current, input current here. So hence, here the collector current is represented as beta times of IB plus 1 plus beta times of ICB. So if you neglect the reverse saturation current, that is very small, then IC shows that approximately equal to your beta times of IB. But here, what is the beta here? Beta is always larger value here. Why? Because of suppose. So this beta is related in terms of your DC current gain of common base configuration. What we taken here, beta is represented as alpha by 1 minus alpha. If alpha is a 0.98, then what happens to beta value? Beta is equal to 0.98 divided by 1 minus 0.98, that is equal to your 49. So in general, the beta is a very large value here. So hence, a faithful amplification is done through this common emitter configuration here. So, and by this representation, the collector current is defined in terms of DC current gain along with your input current here. Now we'll see that the characteristics of this common emitter configuration, and we know that whatever the configuration the BJT contains, the two types of the characteristics here. One is input characteristics, another one is your output characteristics here. Yeah. So it is represented as in a common emitter configuration. One is the input characteristics, means across the input junction, we need to observe the parameters here. Then we need to plot the graph between those two measured parameters here by making the output is a constant. Similarly, we need to identify the parameters across the output junction, and that indicates the characteristics of the output of your BJT under the common emitter configuration here. Now, if you want to see that the input characteristics here, so and here I use some devices to measure the input parameters as well as the output parameters here, and then we need to use the same biasing approach. And input side, we need to follow that input junction should be forward biased and output junction should be your reverse biased here based on the transistor. So here I use this NPN transistor, and this is the base, collector, and this is the emitter. And material is this N-type material, base is the P-type, and the emitter is again N-type material here. So hence P is connected to positive for the battery to make this emitter base junction is a forward bias. And then across the emitter side, if you want to plot the characteristics, we need to plot the graph between input voltage and input current. So what is the input voltage from this configuration? The voltage is measured between base and emitter, that is represented as your VB. And the input current is measured across the your input current, that is represented as your IB. So now to plot this input characteristics, then by making the output parameters are your constant here. So which one is the output parameter here? By making this VC is a constant here, we need to observe the input characteristics in between VB versus your IB. Now you can see this, if the input is, when let us take this VCC is a 0 here for this case. So now, and with respect to your output voltage, by making the output is a constant, we need to plot the input characteristics here. In the first time, I consider that when VC is a 0, so what happens when VC is a 0 here? So means the input side, it looks like normal PN junction diode, then it satisfies the PN diode characteristics here. Means your applied input voltage, it just crosses the current voltage, then conduction rate is your increases. But what happens when VC is greater than 0? So when VC is greater than 0, and let's take, and this is your NPN transistor N, this is the P and N. This is the normal depletion region is a formed while when making the VC is a 0. And now this is the base here. This is the base. Base is acts as the input. And in between, we apply this is the reverse bias. So N is connected to positive with respect to base. And the VC is increased from the 0. What happens here means that your reverse voltage is increases. If the reverse voltage is increases means your depletion layer is also increases. And based on the doping levels, and more depletion region is penetrates toward the base compared with your collector. So that is the reason. When VC is increased from 0 and more depletion region penetrates towards the base compared with your collector here. So let us case, this is the depletion layer is formed when VC is increased from 0 to some certain voltage here. If you observe this one, when the VC is increased from the 0, so what happens here? The base width is a decreases here. So if the base width is a decreases, then the number of charge carriers are also decreases. So in this case, to allow the same conduction when the VC is a 0, we need to apply a large amount of the force here. So that is the reason the curve shift towards the right side of this region. So to allow the same current when VC is a 0 and when VC is a greater than 0. But here what happens, it requires some large amount of the force. Why? Because of that, the base width is decreases here. So that is the reason to allow the same amount of the conduction under when VC is a 0 and VC is increased from 0. It requires a large voltage compared with your VC is a 0. That I shown here, that is your input characteristics of your common emitter configuration. Similarly, if you want to plot the output characteristics here, so means to observe the output characteristics, so we need to plot the characteristics between output voltage and output current by making the input is a constant. So means that input means we need to maintain that IB is a constant. But means here we need to plot the characteristics between VCE versus IC by making this IB is constant here. But we know that one relation. So what is the relation in a common emitter configuration? In a common emitter configuration, it is represented as IC is represented as beta times of IB plus 1 plus beta times of ICBO here. So we analyze this mathematical relation from the common emitter configuration. So that is represented as IC is represented as beta times of IB plus 1 plus beta times of your ICBO here. So if you assume from this relation, if the reverse saturation current is very small compared with your base current, let this IC is approximately equal to your beta times of your IB. And here we know that beta is and IB is a very small current, but beta is a large value. Already we observed that if alpha is considered as 0.98, then beta is a changes towards 49 here. So hence this is 49. Suppose if I consider the alpha value is 0.98, So what happens here? This is 49 times of your given input current here. Means more amplification is done in your common emitter configuration here. So that is the reason. We need to identify the the output characteristics with respect to your by making the input parameter is your constant. But here it satisfies the DC current gain in terms of your beta value here. Hence, so here I shown that the output characteristics between VCE and your IC means x-axis is represented as a VCE and the y-axis is represented as your collector current or output current that should be measured in terms of your milliamperes by making that your input current is a constant here. So this is input current here, IB is represented here. So why here I represented this IB is micro means I base current is a very small. Why? Because of the based on the doping levels and whatever the charge carriers are emitted from the emitter. So only the 2% to 5% of the charge carriers are constituted with the base and the remaining charge carriers are constituted with your collector. So that is the reason the base current is a very small compared with your collector current here. So hence the small current is here measured in terms of your microamperes here. And similarly, if you observe at the output side, so what happens at the output side? The output junction is a reverse bias here. So hence, that particular output junction is a reverse bias means that the output voltage is proportional to your biasing energy. So why? Because of that, we know that when particular PN diode, let us take this is the PN diode. So the PN diode is operated on the reverse bias means P is connected to negative pole of the battery and N is connected to positive pole of the battery. Then here, so what happens here? Now across this PN junction diode, now we are going to output voltage V0 here. So when the PN diode is operated on the reverse bias here, then it does not allow the flow of conduction. Hence, it looks like it acts as an open circuit. Hence, this particular PN diode is replaced with the open circuit. Now here we apply some amount of the biasing energy. Across this diode, we are going to absorb the output voltage. So from this equivalent circuit, this V0 is proportional to your applied input voltage is V. So that is the reason. You can observe this one here. The VCE is approximately equal to your applied energy is your VCC here. So why? Because of that, your output junction is your reverse bias. So this is, now it becomes your IC is equal to beta times of your IB. So if beta is considered some approximately equal to 50 and if IB is suppose 20 microamperes, so then what happens here? I see 50 into 20 microamperes here. So means this is 1000 microamperes. So that is the reason the current is increases like this here. So this one when IB is a 20 microamperes here. So for this is IB is a 40, then current is again increases here. So this is a characteristics is drawn between VCE versus your IC by making this IB is a constant. So what happened this one? This factor is a large slope. Why this large slope is increases means a very small change in alpha value, a large change will occur in a beta parameter. Means a very small change in a DC current gain of common base transistor means that alpha value. A large change will be observed across the current gain of the common emitter configuration. So that is the reason a large slope will be formed generated in this common emitter configuration here. Clear? So up to this point, we observed that the common emitter configuration with respect to the characteristic, that is input characteristics of common emitter configuration as well as output characteristics of common emitter configuration. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.